Einstein was incomplete. Or at the very least, the version of Albert Einstein that's printed on, a million coffee mugs and high school posters is missing half the story.
Yeah, we really treat E equals mc squared like this untouchable monument.
Right. The scientific world points to it and says, like, there's the ultimate flawless truth of the universe.
Which is natural. I mean, we crave that kind of simplicity. Reducing the entire cosmos to 3 little letters and a number gives us this sense of control over a universe that is terrifyingly complex.
But when you actually step into the modern world of quantum physics, that clean, iconic equation starts to crumble.
It really does.
We are looking at a physical landscape right now that is fundamentally incompatible with the classical understanding of E equals mc squared. So welcome to this deep dive.
Glad to be here.
Today, our mission for you is to take everything you thought you knew about the most famous equation in human history and completely dismantle it. And then we are going to rebuild it from the ground up.
And to do that, we brought in a massive stack of sources.
Huge stack.
We're looking at intense historical debates from physics forums, digging into modern quantum mechanics textbooks, unpacking cutting-edge papers from the journal Frontiers on something called generalized uncertainty.
And finally, exploring this mind-bending new framework known as the timeless energy principle.
Right. We are going to explore the historical mistakes Einstein actually made in his early proofs.
Which is wild to think about.
Yeah, and we'll tear down the pervasive myth of relativistic mass, figure out why the quantum realm forbids any particle from ever truly being at rest.
And eventually synthesize all of this into a completely new mathematical framework where time itself might just be an illusion created by energy. Okay, let's unpack this.
Where do we start?
Well, to understand why the equation is incomplete, we have to look at the messy way it was historically constructed. I was reading through the historical analyses and the physics forums, and get this, it turns out Einstein published 7 different proofs of mass energy equivalence over his lifetime.
7 proofs.
Yeah. And according to modern physicists, every single one of those 7 proofs contained a mistake.
I mean, the early 1900s were basically a wild west for physics.
All right.
Before the theory of relativity was fully baked, scientists were hauling around a massive amount of conceptual baggage. You had brilliant minds like Poincaré in 1900,
right,
and later Lewis and Tolman in 1909, trying to force these bizarre new relativistic concepts into old, comfortable Newtonian boxes.
And that friction resulted in what physicists jokingly call the Gang of Four masses.
Yeah, they were using these archaic terms like longitudinal mass, transverse mass, rest mass, and relativistic mass.
Relativistic mass is the one that really gets under my skin, because you still see it everywhere.
Oh, absolutely. Textbooks, popular science articles, YouTube videos.
They all claim that as an object moves faster, like closer to the speed of light, its mass literally increases. But looking at the paper by Level-Kuhn in our sources, this seems completely misleading. Let me try to break this down with an analogy, and you tell me if I'm tracking here.
Go for it.
Let's say I take a flat iron and I plug it in until it's heated to, say, 400 degrees. The atoms inside that iron are vibrating intensely with thermal energy.
Okay, yeah.
Does the iron get heavier?
Technically, yes.
Yeah.
The iron's invariant mass, like its true structural mass, does increase by an infinitesimally small amount. You've added internal rest energy to the system by heating it.
Right. But what if I take that same iron, unplug it, let it get ice cold, and then just throw it as hard as I can across the room?
Ah, that is the critical distinction. Its kinetic energy changes relative to the person watching it fly by, but the iron itself does not gain mass just because it's moving through space.
So it's not actually getting heavier.
Exactly. The concept of relativistic mass, which calculates mass by taking total energy and dividing it by the speed of light squared, is considered an absolute relic today. Modern physicists on the forums, like this user Peter Donis, flat out call the term gobbledygook.
I love that. I love that a physicist used the word gobbledygook.
It's very fitting.
But I'm slightly confused. If relativistic mass makes the math work out so that momentum is conserved, why do modern physicists hate the term so passionately? Like, what breaks if we use it?
It breaks the entire underlying geometry of space-time.
Oh, wow. Okay.
Yeah. In general relativity, mass is supposed to be a Lorentz invariant.
Yeah.
That's just a fancy way of saying mass is a fundamental property of an object that every single observer in the universe must agree on.
Regardless of how fast they are moving.
Right. If mass changes with velocity, then your mass depends entirely on who happens to be looking at you.
Wait, so if I'm standing still, I weigh 160 pounds to someone standing next to me. But to a spaceship flying past Earth, my mass is suddenly entirely different?
Exactly. And the math gets infinitely worse if you try to use that shifting mass to calculate acceleration.
How so?
Well, if you plug relativistic mass into Newton's old F equals ma formula, you get different answers depending on whether you push the moving object from behind or push it from the side.
That makes no sense.
Right? The resistance changes based on the angle.
Right.
It turns the elegant geometry of space-time into a contradictory nightmare. What's fascinating here is that Einstein actually knew this.
Which explains a detail I found deeply fascinating in the sources. In a 1948 letter to Lincoln Barnett, Einstein himself explicitly rejected the idea of relativistic mass.
Yeah, he didn't like it at all.
He admitted it is not good to introduce the concept of the mass of a moving body, saying it's better to just talk about momentum and energy. He hated the very concept his equation supposedly birthed.
And consider the pedagogical tragedy of that. Despite Einstein's own explicit rejection, this archaic concept survived in the educational system for decades. Teachers used it as a crutch because it made relativistic math look a little bit more like the comfortable Newtonian math students already knew.
Which led to Carl Adler's famous 1987 paper titled, "Does Mass Really Depend on Velocity, Dad?"
I love that paper.
Yeah, a young boy asks his physicist father this question, and the father has to reply, "Actually, no, but don't tell your teacher."
It's sad, really. We spent a century teaching a mathematical illusion because it was easier than explaining the true reality of the physics.
So if we strip away that illusion of relativistic mass, we are left with invariant mass, true mass,
Right.
the mass of an object when it is sitting completely still. Which brings us right back to the monument E equals mc squared.
Exactly.
That equation specifically calculates the energy of a particle at absolute rest. But our sources point out a fatal flaw when we drag this equation into the modern era. In quantum mechanics, nothing is ever truly at rest.
This is the exact intersection where classical physics and quantum mechanics violently collide.
Because E equals mc squared assumes a particle has a momentum of exactly zero, right?
Yes, but the bedrock of quantum mechanics is Heisenberg's uncertainty principle. You cannot simultaneously know a particle's exact position and its exact momentum.
Help me visualize the mechanics of that. Let's say I have some sort of futuristic quantum speed camera.
Okay.
And I use it to measure a car speed so flawlessly that I know its momentum is exactly, perfectly zero. What happens to the car?
Mathematically speaking, a particle's quantum wavelength is inversely proportional to its momentum. If the momentum is exactly zero, you are dividing by zero.
Uh-oh.
Yeah, the wavelength becomes infinite. In your speed camera scenario, the moment you confirm the car's momentum is exactly zero, the uncertainty in its position becomes infinite.
Wait, really? So where is the car?
The car's physical form would smear across the entire universe. It would be everywhere and nowhere simultaneously.
A completely unphysical, impossible situation.
Exactly.
So to avoid being smeared across the cosmos, what does the particle do?
It jitters. According to the quantum mechanics textbooks we reviewed, quantum particles always possess a microscopic jitter.
Even at absolute zero.
Even then, when you cool them down to their lowest possible energy state, they still possess non-zero kinetic energy. We call this zero-point energy.
Therefore, a perfectly resting mass, the fundamental requirement for E equals mc squared to work, is a classical fiction.
Correct. Which means there is a real, complete equation that physicists actually use, and it's much longer.
I won't read the whole string of algebra, but from looking at it, it basically says that an object's total energy is a combination of its mass energy, A and D, its momentum energy.
That is the true equation that respects the four-dimensional geometry of the universe.
Right.
To see why it matters, just look at a photon, a particle of light. A photon has zero invariant mass. If you plugged a photon into just E equals mc squared, the math says it has absolutely zero energy.
But light obviously has energy. It heats up the planet.
Exactly. But in the true expanded equation, E squared minus PC squared equals mc squared squared, the mass portion drops to zero, and you are left with the momentum portion. A photon's energy comes entirely from its momentum.
Okay, so the universe is jittery. Quantum particles are always moving, fluctuating, refusing to sit still. But Einstein's other masterpiece, general relativity, our theory of gravity, relies on smooth, continuous, predictable curves in space-time. How does gravity, which wants smoothness, interact with a quantum particle that is constantly jittering?
That is a multi-million-dollar question keeping physicists awake at night.
I bet.
To bridge that gap, researchers in the Frontiers paper by Marletto and Vedral looked at the equivalence principle.
Remind me of the classical definition there.
Classically, Einstein said that standing perfectly still in a uniform gravitational field like you and I sitting on Earth right now is completely indistinguishable from being in a rocket ship accelerating upward in deep space at 9.8 meters per second squared.
So gravity and acceleration are identical. But here's where my brain starts to hurt. What if the particle isn't just sitting there or falling? What if, thanks to quantum mechanics, the particle is in a superposition?
Oh, this is the good stuff.
Right, meaning it is simultaneously freely falling, A and D hovering stationary in a gravitational field at the exact same time. How does gravity pull on something that is in two completely different states of motion?
Well, gravity doesn't just pull on the object. Gravity warps time.
Okay.
The researchers proposed that the equivalence principle must apply to each individual branch of that quantum superposition independently.
Independent branches.
Yeah. So imagine you take a super chilled blob of atoms acting as a single quantum entity, like a Bose-Einstein condensate, and you put it into that dual state. One branch of its reality is freely falling. The other branch is held stationary, feeling the full pull of gravity.
And because the stationary branch feels the gravity, its local clock ticks at a slightly different rate than the freely falling branch.
Exactly. Time diverges for the two states. And when the experiment forces those two branches of the wave function to recombine, they don't line up perfectly anymore.
That makes sense.
That difference in the flow of time creates a highly specific, detectable interference pattern. The math shows this phase shift is proportional to the time cubed. It's called the Tet cubed phase shift.
Wow.
And incredibly, using highly sensitive quantum measuring devices, experimentalists have actually detected this shift.
They caught gravity warping time across a single particle's split reality. That is staggering.
It really is.
But wait, does this actually solve the clash between relativity and quantum mechanics? Because it sounds like they just proved gravity works on quantum stuff.
It is a remarkable achievement, but it's a bit of a Pyrrhic victory.
Why?
If we connect this to the bigger picture, the experiment still relies on treating space and time as a fixed classical background. It doesn't quantize gravity itself.
Ah, I see.
When theoretical physicists try to truly merge the two to write a theory of quantum gravity, they run into devastating mathematical paradoxes.
Right, because if you zoom in close enough, the smooth fabric of Einstein's spacetime should logically break down into a bubbling quantum foam.
Exactly. Physicists assume there has to be a minimum length to the universe.
Yeah.
The Planck length. You can't zoom in infinitely.
But the sources point out that when physicists tweak the standard mathematical rules to foist this minimum length into existence, the math goes completely off the rails. It creates something called the soccer ball problem.
Yes.
Walk me through the mechanics of that, because the name is deceivingly playful for something that breaks physics.
To enforce a minimum length, physicists tried modifying the commutators, which is essentially the algebraic rulebook for how quantum properties like position and momentum combine.
Okay.
When you apply these modified rules to a single tiny particle, everything works fine. You get a minimum length.
So far, so good.
But when you try to scale those rules up to a multi-particle object, say 10 to the 23rd power particles bonded together into a macroscopic soccer ball, the uncertainties multiply catastrophically. The minimum length scales up with the mass.
Meaning a macroscopic soccer ball would suddenly have a massive, noticeable fuzziness to its physical location that we obviously don't observe in the real world.
Precisely. The rules of physics suddenly break down. You violate Lorentz invariance, meaning the laws of physics change depending on your frame of reference. The models become entirely pathological.
Pathological math is never a good sign. So if modifying the algebraic rules creates giant fuzzy soccer balls, how do modern physicists solve the need for a pixelated universe?
The Frontiers paper by Lake and his colleagues proposes a brilliant shift in perspective.
What do they suggest?
Instead of breaking the fundamental algebraic rules of motion, they suggest we change how we mathematically treat the act of measurement itself. They utilize something called POVM's positive operator valued measures.
I had to read that section 3 times.
It's dense.
Let me see if I can translate this into a visual analogy. Tell me if I'm off base here.
Okay.
Using POVMs is like accepting that the universe has finite accuracy baked into its lens. It's not that our tools are bad. It's that space itself has a minimum sweet spot of resolution.
I like where this is going.
Imagine the universe as a high-definition video game. If you try to zoom in past a certain point, you don't find smaller and smaller details. You just hit the base pixels of the game engine. POVMs are the mathematical tool that handles that inherent pixelation without breaking the game's physics engine.
That is a phenomenal way to visualize it. By framing the limitation around the measurement rather than the motion, the standard Schrödinger and Heisenberg equations remain completely untouched.
So you avoid the soccer ball problem entirely.
Entirely. The macroscopic world behaves normally, but you still naturally derive a universe with a minimum Planck length.
So let's look at where we are. We've shown that E equals mc squared is based on a flawed classical premise of rest.
Right.
We've established that particles constantly jitter, that gravity warps time across quantum superpositions, and that space-time itself might just be fundamentally pixelated.
It's a lot to take in.
It is. And this sequence of cascading revelations leads us to the most mind-bending source in our entire stack, the timeless energy principle, or TEPEP. Because if you can't trust mass, and you can't trust smooth space, and you can't trust the continuous flow of time, what is actually left?
Energy. The timeless energy principle argues that energy is the only fundamental reality.
Yes, to energy.
Yes, space and time do not exist at the absolute basement level of the universe. They are not the empty stage upon which events happen.
Then what are they?
Instead, time and space emerge from a pre-temporal, timeless substrate of pure energy.
Okay, my brain is officially melting. So what does this all mean? Time is an illusion created by energy. How does the math for that even function without turning into pure philosophy?
The TEP framework actually rewrites Einstein's energy equation conceptually. Imagine the new equation has three distinct pieces. You still have a piece representing momentum, you still have a piece representing mass.
Okay, that sounds normal.
But in this new formula, the mass piece is attached to a mathematical dimmer switch. The paper calls this the mass activation function, and it is entirely controlled by the flow of time.
Wait, how does time control mass? What flips the switch?
Decoherence. Think of decoherence as the process of quantum possibilities interacting and locking into a single reality, like the video game engine finally rendering the graphics on your screen.
Oh, I see.
At the absolute deepest quantum level, before any interactions happen, time hasn't emerged yet. Because time is zero, that mass activation switch is turned entirely off. Mass literally does not exist.
So mass is just the game rendering once time turns on.
Essentially, yes.
Yeah.
As quantum interactions occur and decoherence happens, a process that takes a microscopic fraction of a second time emerges. As time begins to flow, the dimmer switch slides up and mass is activated.
That is heavy. But there's a third piece to that TEP equation we haven't touched on, right? A piece representing vacuum energy or substrate energy shifts?
Yes, and that piece is the true game changer. In classical relativity, the vacuum of space is mostly treated as empty nothingness. In TEP, the vacuum is boiling with this timeless substrate energy.
And this isn't just theoretical navel-gazing. The sources are adamant that this TEP equation actually solves real, observable astrophysical mysteries that classical relativity completely fails to explain.
Exactly. Dark energy is the perfect example.
Right. We look out at the cosmos and see galaxies accelerating away from each other, and standard relativity has no mechanical explanation for it. They just slap a mathematical band-aid on it called the cosmological constant.
But in TEP, dark energy isn't magic. It's just a macroscopic physical manifestation of that boiling, timeless substrate energy pushing outward.
It also provides a lifeline for black hole physics, doesn't it?
It does.
Yeah.
Near the event horizon of a black hole, the gravitational pull is so extreme that the standard rules of spacetime warp severely. TEPA predicts that in those extreme environments, the substrate energy introduces massive corrections to the math.
Meaning it could entirely alter our understanding of how black holes evaporate.
Yes, potentially preserving quantum information that classical relativity insists should be destroyed forever.
It even rewrites the origin story of the universe. In the standard Big Bang model, physicists had to invent a concept called cosmic inflation, this brief, magical period where the universe supposedly expanded faster than the speed of light.
All just to explain why the background temperature of the universe is so incredibly uniform everywhere we look.
Right. But if time doesn't exist fundamentally, as TEP suggests, then in the pre-space-time phase of the early universe, energy could propagate and equalize instantaneously.
The entire universe was already connected before the clock of time even started ticking.
You don't need inflation at all.
Exactly. And consider what that actually means for Einstein's legacy. If the timeless energy principle is correct, Einstein wasn't fundamentally wrong. He was just observing the universe in its emergent time limit.
What does that mean practically?
Once the quantum dust settles, once decoherence finishes rendering the universe and time starts ticking normally, that dimmer switch gets locked to 100%. the boiling vacuum energy becomes negligible for everyday objects.
Hmm.
The incredibly complex TEP equation collapses downward and simplifies perfectly into the familiar mathematics we've used for the last century. Einstein was just looking at the calm, flat surface of an incredibly deep, churning quantum ocean.
What an incredible journey this stack of sources has taken us on. We started by dismantling a monument.
He really did.
We looked at Einstein's flawed proofs and realized that the archaic idea of relativistic mass, the idea that a moving iron gets heavier, was just a pedagogical lie we told students to make the math easier to swallow.
From there, we dove into the quantum realm, discovering that Heisenberg's uncertainty principle outlaws the very concept of rest. Because a particle with zero momentum would smear across the cosmos, everything must possess a zero-point energy jitter.
Then we threw those jittering particles into a gravitational blender. We saw how gravity warps time differently across superpositions, creating detectable phase shifts.
But to prevent the math of space-time from breaking into pathological fuzzy soccer balls, we explored POVMs, the mathematical proof that our universe has a finite, pixelated resolution built into the very act of measurement.
Which ultimately delivered us to the timeless energy principle.
The profound realization that mass and time are not fundamental pillars of reality, but are activated, emergent properties bubbling up from a timeless substrate of pure energy.
It completely reframes how you view reality. The next time you're at a party and someone casually drops E equals MC squared to sound intellectually deep, you now have the conceptual ammunition to explain why their coffee mug is a relic of classical physics.
A relic that barely scratches the surface.
Right. It barely scratches the surface of the timeless, jittering, quantum reality we actually inhabit.
As we close, I want to leave you with one final lingering implication drawn directly from these sources.
Let's hear it.
If energy is the only true fundamental reality, and if time itself is merely an emergent byproduct, an illusion created by the quantum decoherence of that energy interacting, what does that make your conscious experience of this exact present moment?
Oh, wow.
As you listen to these words, are you actually moving forward through a physical river of time? Or is time simply a localized illusion, a narrative sequence rendered into existence entirely by the energy of your own observation?
Suddenly that simple, clean equation feels a whole lot messier.